Good morning, everybody. How's everybody doing? Good, bad, somewhere in between. If you can, because nobody has their camera on right now. You put your camera on so that at least I can get some sort of visual feedback. You can like shake your heads, yes, no. It helps me to like know whether I gotta like repeat something. Thanks. All right. I know it's not 9:30 yet. But just so that everybody knows, Thursday is one of those random university holiday break day thing. I think they're calling it. So we won't meet in person. So I mean, you can show up if you want, but I won't be there this Thursday. Sounds good. Cool. All right. A few other things. Let me see. So I mentioned earlier, but I'll say it again. There was a typo in the Jupyter notebook in this little code cell here just before exercise 6. Um, and I posted the correction on their forums. So this is what the old code was, and this is what it should be. So if you were getting an answer that didn't agree with the textbook, no, the textbook's not wrong. No, the computer is not wrong. I was wrong. I forgot to square side, right? And we'll actually talk about this today. We haven't gotten this far in class yet, but yeah, I just forgot this part of the code and this part of the code right here. So yes, yeah. So there's a typo there. So when you get to this part, make sure you correct it with this instead. All right, is there like a weird glitch in the top of the screen? Yeah, I don't know what's happening. Was
Yeah,
there?
I think it's the green screen. Uh,
Hmm. Was that there before, or did that is that new for today?
I think it's the first time I've seen it, but I don't know.
Hmm. Well, I'll hope it goes away. I don't know what to do right now. The second thing is I'm creating the study checklist because I was thinking if I were to study for an exam, oh, it's pretty bad, isn't it? Um, Hang on, let's see. Maybe I fixed it. If I were to study, nope, it doesn't matter. Hang on, let's try it this way. What am I doing? I forgot. There we go. So I'm hoping it goes away. So if I was studying for an exam, I would like a checklist of things that I should know. And so I created this checklist. It's not complete because the exam's on next Thursday. So I don't know how far we'll get. But I'm planning to finish this up and post it somewhere on ACE by Friday, by the end of the Friday, so that you have a week or so to, you know how to study, basically. I like things like this. So hopefully you find it useful too. And secondly, I'll also update this little thing that I made with end of chapter practice problems for questions from chapter 12. So like these two here, along with your notes, should act as a good study guide. And if you have questions and stuff like that, you'll let me know. But I am in the process of writing that first exam. So yeah, should be fun. We'll see. Any questions about that so far? Nope. The other thing I wanted to mention was this little equation sheets. I forgot where I put it. It's under important documents, equations and constants sheet. If you haven't printed it out, please do so. It's very, very useful. And well, I took a long time typing it, so hopefully it's useful. If you printed it before today, I added these two equations to chapter 10. You can write that in if you haven't printed it yet. Fine, great, it's there. You can print it. But yeah, it's all basically this is what you'll have for the first exam. I'll give you this. I'll print one out for each of you, and I'll probably collect it back so that we can use it in future exams. I don't know. Um, save some paper. But yeah, if you're wondering what you'll have for the exam, it's this. Like all the equations you could possibly need. You don't have to memorize any of them because memorization, like, what's the point? Um, yep, sounds good. Any questions about any of that?
Do you have any details about the format of the test yet?
Well, I'm still writing it, but what I'm thinking is sort of somewhere between a third or a half of it is just going to be sort of short essay questions. So, for example, when I say describe when it is best to use Newton's Lagrange and Hamilton's equations of motion, that could be, I don't know, that could be a nice essay question. Like in 3 or 4 sentences, talk about each of the, something like that. So, right, solving one of those, that looks like a nice math problem, right? So, I would say a third to half of it would be essay, and half to 2/3 of it would be math based. I know that's some weird ratios, but uh, I haven't written the questions yet, so I'm not quite sure where the balance would lay. Sounds good. And it's not going to be anything too scary. I'm going to basically look at questions that we've done in class and questions at the end of the chapter that I give you to practice on, and just make variations of those. Is how I'm going to do this. So, if you can answer all the questions well enough, you'll be fine. Sounds good? Awesome. And if you have questions, let me know. Yeah. Like, and don't stress too much about it. It's a PChem exam. It's supposed to be hard, but I'm gonna curve the class at the end. If it ends up being that bad, and I'm hoping it's not, I'm gonna end up curving anyway. So don't stress too much. But you should study. I mean, right? All right. If you have questions throughout the week, just let me know, or you can actually ask them in forums because other students might have the same questions about exams too. All right. So let's do some brief recap on what we did last time, and I don't even remember what we did last time. So let's see. Well, two lectures ago, right? We started talking about the postulates, right, of quantum mechanics. Postulate number one, I always like to go over from the beginning, but postulate number one talked about the wave function. Postulate number two talked about operators relating to observables. And postulate number three talked about how the only observable you can get from the wave function comes from eigenvalue equations, right? Where k here is a constant. So if it's not an eigenvalue equation, you cannot observe it. So this is for the only observable.
Dr. Chulai, we can't see anything you're writing at the moment.
Oh, yeah, no, that's right. I can't see anything I'm writing either. What's going on? Hang on. Thanks for saying that. um, ah, hmm. Let's see. You see my little face though, right? Like,
Yeah, we can see you, just not anything you wrote.
Yeah, and you're not frozen either, so.
yeah. Oh, the joys. Why am I having so much technology issues today? Oh, looks like we're in business. Can you see it now?
Yeah.
Awesome. So let me keep this little window here so I can see both your reactions and what I'm typing. All right. So that's what I was talking about. Postulate number one is the wave function. Postulate number two is the fact that observables are related to operators. And postulate number three, where the only observables that we can observe, I guess, come from eigenvalue equations. And we did some practice about how to set up eigenvalue equations and how to recognize them. As long as you get the same wave function back again times some constant, that's an eigenvalue equation. Anything else, not an eigenvalue equation, which means you can't observe it. So what this led to The postulate number 3, what it naturally led to was the uncertainty principle, right? And the uncertainty principle we talked about where two different observable or two different operators, and in the most common example is position, right? Which is just x dot, and momentum, which is this negative I h bar ddx, I think, I forgot. They cannot be part of the same eigenvalue equation because there's no function where this guy is an eigenfunction with this operator and also with this operator. So just because of this fact that you can't have the same function be part of an eigenvalue problem with both of these operators at the same time, it sets up the uncertainty principle, right? And in the uncertainty principle, we just have this equation. The uncertainty in the position times the uncertainty in the momentum is greater than or equal to h bar over 2, where h bar was h over 2 pi. Again, I'm writing all of this from memory. I'm just trying to, I hope I'm writing all of these equations right. So far they look right. Okay, and since mass can never be uncertain, the uncertainty in momentum can actually be written as the mass times the uncertainty in the velocity. All right, I'm trying to think, what else did we do last time? That might have been it. And then
Started
we
talking
started
about the interpretations of
yes, thank you. Yep, I just remember that one. And then we started talking about the interpretations of quantum mechanics and the wave function. And there's a whole bunch of them, and I asked you to go read about some of them, and I hope you did because they can be really fun just to learn that sort of thing. But the one that we're focused on is the Born interpretation, and I think that's where we sort of left off. And in the Born interpretation, Born said the wave function is all about probabilities. Whether or not he's right, is another thing. But it's the only one of the interpretations that are useful to us from a sort of mathematical perspective. The others are fun to think about, but they don't really help us to solve anything, at least not yet. But in the Born interpretation, he says that this quantity here, psi star psi, is related to probability, right? And in fact, the equation for it is the probability is equal to the integral of psi star psi d tau over all space. Well, actually not all space, sorry. Between regions A and B, where regions A and B are the regions you want to find the probability for. So that's the regions for probability, right? I mentioned that star means complex conjugate. And all this means is change I to negative I whenever you see it. So if the wave function was something like e to the minus I kx, right? If that's psi, then psi star, right, would just be e to the positive I kx, right? That's just what psi star means. Complex conjugate more generally means, let's say you have a number like 5 plus 3i, right? That's a complex number. The complex conjugate for this is going to be 5 minus 3i, right? Complex conjugate. Basically, the imaginary part just changes sign. All right. So what else do we have? I mentioned that tau just is a placeholder for any space, right? So tau is a placeholder for x, y, or z, or dx, dy, dz, or combinations of any of that. And that's the probability. So this is an equation, and I don't know, I'm hoping throughout this course you develop an appreciation for, you see an equation and you can start to think what that equation means in a more sort of visual, practical sense. But here's how we might develop that sort of skill. So let's figure out what this equation actually means from a graphical point of view. So let's say we have a graph, right? This is x, right? And that this is who knows what. We'll just keep it there. Let's say you have some wave function. I'm going to draw some random wave function. I don't know. That's my wave function. I'll call it psi. Right? Let's say I want to find a probability between this region, let's call that A, and this region, this point B. So we want to find what's the probability of this particle in this region. Well, this equation says we're going to integrate psi star psi, right? So in this example, psi is just real, right? We're not worrying about the complex part. So psi star psi is just the same as psi squared, right? Everybody with me? So let's see what that might look like. So if I take the square of something, just makes it larger and all positive, right? So if it's negative, it becomes positive, right? If it's positive, it becomes bigger positive, like that. So this is what psi star psi would look like. I'm just giving a random example, right? And so if you're integrating, remember integration means area under the curve. So if you're integrating that, you're finding the area of this region here, right? And that area is the probability.
Quick question.
Yep.
At some point, can we go over like the imaginary portion of graphs? Because I know for example, haven't talked about imaginary numbers since like sophomore year of high school.
All right.
So I don't remember much about them.
That's okay. Nobody does. So we could do that now. So in all of these examples, psi was just real. There was no imaginary part because I only have one axis to draw, and so I'm going to draw the real part. And this is way more math than like we would go into this course, and I'm not claiming to be some, I don't know fancy math, right? I just know the math that I know. But imaginary numbers you can think of as a, okay, this is gonna go way too much into math theory, so please stop me if any of this seemed too confusing, because none of it is necessary for the course. But you can think of this as the imaginary axis as perpendicular to the real axis, right? So in this example here, this y-axis that I drew was a real axis, right? And so psi is real, it can be positive, so it'll be above the 0 line on the y-axis, and it could be negative, it could be below the 0 line. The imaginary part is perpendicular to that, meaning it will run in this, if I were to draw it on this page, it will run in and out of the page, right? So if there is an imaginary part, it'll be in and out of the page. That's really the simplest way to think about imaginary numbers. People just use it for another dimension, if you will. Yeah, that interacts with the real dimension. Again, it's way too much into math theory that you would need to know, but just know that when you have I multiplied by I, you get -1, right? If you have a situation like x plus iy, right, and there's x minus iy, when you multiply these two things together, I think you just get x squared plus y squared, I think. Yeah, because basically when you have, let's do it part by part. X times x, right, will give you x squared. X times -iy will give you minus ixy. This part will give you positive ixy, which would cancel out. And then this times this will give you positive y squared. So just remember how to add complex numbers and how to multiply complex numbers. If you have 5 plus 3i plus 6 plus, I don't know, 4i, when you're adding, you just add the real parts, right? So 5 plus 6 becomes 11, and then you add the imaginary parts. 4 and 3, that becomes 7i. Yeah.
Okay, thank
So,
you.
You're welcome. If you have any questions about these sorts of things, just let me know. But for now, just try to remember how to add and multiply imaginary numbers. Everything else is not really necessary. I know that's to put it bluntly, this is not a math class, and just using imaginary numbers is what we're going to be interested in. But if we're looking at this Born equation again for probability, basically what this equation does is find the area under this curve of psi star psi, and that area is the probability. Everybody with me? All right. So let's do some for practice, right? So let's say we want to find the probability of a particle with, let's say its wave function is psi, it's a function of x, is I times the square root of 2 times cosine of pi x between x equals 0 and x equals 0.1. I'll do this one for you. Not that I don't think you can't, but you know. So the first thing that we need to do is find psi star, right? Because we have psi, but we need psi star. And like I said, we just look at where the I is and we change it to negative I. So that becomes negative I square root of 2 cosine pi x, right? So now the probability, right, is equal to the integral. They tell us the region between x is equal to 0 and 0.1. So 0 and 0.1, those are our limits of integration. It's psi star times psi. So here's where knowing how to multiply complex numbers comes in, right? So we're looking for this, psi star psi dx. I changed tau to x because that's the only dimension we have. So let's get this part here, psi star psi, right? So for psi star, we have this negative I, and it's going to be multiplied by this positive I, right? So I times negative I. So I times I is negative 1 times this negative becomes positive 1, right? Do we see that? So this negative I times this positive I just becomes 1. All right. Square root of 2 times square root of 2 becomes just 2, right? Square root of 2 times square root of 2 is just 2. And then cosine pi x times cosine pi x becomes cosine squared of pi x. So then our probability becomes the integral. Sorry?
I have a question.
Yep.
So where it says ix minus I equals positive 1, what happened to the x?
Oh, this is not x. Sorry, this is a multiplication symbol.
Oh, okay.
I times negative I is positive 1.
Okay.
So I write my x like this, little curly x's. When I do that, it means multiple. I know it's sometimes hard to distinguish, but straight lines x is a multiplication symbol. Curly x is the x. It's usually how I write it. But yeah, I can put a little dot there for multiplication too. All right, so this is psi star psi. Psi star psi. Saying that fast, it's difficult. All right, so then our probability goes from between the integral between 0 and 0.1 of 2 times the cosine squared of pi x dx, right? Now, at this point, you're probably thinking, how do I do the integral of cosine squared x? But again, I don't need you to remember how to do that. You just look at the integral table, right? And you go up, this is a trig function, so you go to trig functions for integration. and you look for cosine squared, and I'm sure it's here. Like there it is. Cosine squared bx dx is this thing. So in our example, b is the same as pi. So let's go back to my laptop, right? So we know that the integral, if, let's do this, b is equal to pi. So then this integral becomes, right, the 2 is a constant, so we can take it outside. It's 2 multiplied by, it's at x over 2 plus 1 over 4b sine 2bx, right? That's what the little integral thing tells us. And this goes between x equals 0 and x equals 0.1. But we said b is pi in this equation, right? So I'll just change b to pi. And that's our integral. You didn't need to remember how to do any of this by integration by parts or any of that crazy stuff. Yeah, so that's it. So now what we need to do is apply the limits of integration. And so the limits of integration, we basically substitute x equals 0.1 and then we subtract x equals 0, right? Remember how to do that? So we have 2, again, this is a multiplication symbol. 2 times, let's do x equals 0.1. So this becomes 0.1 over 2 plus 1 over 4 pi times sine of 2 times pi times 0.1, right? Minus, we now substitute x equals 0, right? So this becomes 0 over 2, which is 0, plus sine of 2 times pi times 0 is sine of 0. And sine of 0 is also 0, so that becomes 0. So this whole second part becomes 0. Right? So this we just plug into our calculator. Remember, if we're plugging into our calculator, this is radians, right? Not degrees. So make sure you get that down. But once we plug this in, we get that the probability is 0.194 for this problem. All right, so let me go over that. Sorry,
Just
go
to
ahead.
double check our math, should the probability always be less than 1?
Yes, the probability should always be less than 1. And we'll talk about that towards the end, a little bit later too, why it is or should always be less than 1 or less than or equal to 1. All right, so let's look at the steps. They give us a wave function and they give us a region that they want us to find a probability, right? We need to find psi star. Psi star is just changing the i's to negative i's, or if it's negative I, change it to positive I, right? You just flip the sign. So then the probability is the integral over the limits that they gave us of psi star psi dx. In our example, psi star psi was 2 times cosine squared of pi x, right? So we set that up and we found the integral. Again, not a math class, so I don't expect you to know how to do integrals, at least not this complex. So you just look it up on a table. It's that easy. So you look it up in a table, you apply the limits. In this case, the limits for the second part went to 0, so it made it easy. And then you just plug these numbers into a calculator. Sounds good? All right, let's try another one. And again, these examples are always different from what you have in your textbook so that you can see even more examples. But you can try this one. Find the probability of a particle with wave function psi of x is equal to, let's give you a real one, not a complex one. Square root of 2 times pi x, sine pi x, between x equals 0 and x equals 0.2. So spend some time working on that one. And if you don't have the integral sheets printed out, but you have your textbook next to you, I think the integrals are on page 805 in your textbook, or you could just open another tab on your computer to pull up this integral page. So let me know when you're done or if you're encountering difficulties, right? There's a lot of math in this class. I don't know if I want to say sadly, most of science is built off of math. And so I want to get you comfortable using these sorts of math. So if you have questions, please ask, or if you're shy to speak, you can type it in chat as well. If you have an answer, like a numeric answer, you can type it in chat. Yeah. So that way I can know when people are done. Are we really having that much difficulties or? Okay. All right. We're starting to get some answers. I got two answers that are pretty much the same, and then another answer that's different. I think the second and the Spencer, I think you forgot to multiply by the two. And so this 2 out here.
That's exactly what I forgot. Yep.
Oh, yeah, I was guessing, but I thought that might be where it's from. All right, let's just pause and walk through this one, right? So we need psi star. But here's the thing. There's no I in this equation. So there's no signs to change anywhere, right? So psi star is the same as psi. It just becomes, it's just square root of 2 times psi of pi x, right? So a lot of a lot of wave functions you see might just be real. There might be no complex part, no imaginary part, in which case psi star is the same as psi. All right, so then our probability we know should be the integral of between 0 and 0.2 of square root of 2 times square root of 2, right? That's just 2. And again, we can, because 2 is a constant, we can take it outside of the integral. Sine pi x times sine pi x is just sine squared pi x dx, right? So if we look up this integral on the table, so we have to remember that too, right? We look up this integral on the integral table, the integral of sine squared bx, in this case b is pi, comes out to be, let me look at it on my screen, x over 2 minus 1 over 4b, but b again is pi, so I'll just put pi there, times sine of 2bx, but b is pi, so 2 pi x. And it goes between x equals 0 and x equals 0.2. So now we fill in those limits, right? So the limits of x equals 0.2, we'll have 0.2 for x here, right? Divide by 2 minus 1 over 4 pi times sine of 2 times pi times x, which is 0.2, not 1. All right. And then you subtract the, well, then you subtract the other limit, right, over here. If x is 0, this part goes to 0, minus 1 over 4 pi times sine of 2 pi times 0, right? So that will become 2 pi times 0, that's 0. So sine of 0 is 0. So this whole thing goes to 0. Let me know if any of this is moving too fast or too slow. So what we have now is, I can simplify this. This 2 cancels out with that 2 and one of the 2's over there. So it's 0.2 minus 1 over 2 pi times sine 2 pi times 0.2. And if you got to this stage, yay, the rest of it is just plugging numbers into a calculator. But if you do, it should come out to be 0.0486, something like that, as a probability. Are we comfortable with that? Does anybody have any questions? You can ask. Please ask. So the whole trick is to sort of get to this point, right? And to get to this point, you need to figure out what psi star is and then multiply those two things together. And so once you have sine square of pi x times 2, everything from there is just looking up stuff on a table and then plugging in numbers.
I have a
But
question.
yes.
So on our test, do you give partial credit? So say we didn't get the exact final answer, but like our steps are right. Do you give partial credit for that?
Oh yeah, I give lots of partial credit. This is, my tests aren't going to be multiple choice where it's either correct or wrong. I want to see people's thought process. So yeah, I give partial credits. Yeah, I just want to see you like try things, right? By the way, don't ever leave, if you don't know how to solve a problem, don't ever leave it blank on an exam. Because then you can't get any partial credit, right? So try something, anything. Sounds good? So we'll get a chance to do more integrals actually. So I think, was it Aaron maybe asked earlier whether the probability can ever should always be less than 1. And yeah, like probability cannot be more than 1, right? So that brings us to sort of the next topic that I wanted to talk about, right, which is normalization. Right? And so our objectives for this bit is to learn how to normalize a wave function. All right, so we talked about what the wave function means, and there's many different interpretations. But according to the Born interpretation, it doesn't really matter what the wave function means. What's important is the square of the wave function, this bit here, psi star psi. The wave function, who knows what it means? But psi star psi, when you integrate that, or you find the area under the curve, if you're thinking about it graphically, but when you integrate that, you get the probability. So we don't know what the wave function means, but the integral of this sort of psi star psi thing, that's the probability. And now, as you all know, probability can't be more than 100%, right? So probability can't be greater than 100% or 1. Total probability must be exactly 1. Think about flipping a coin, right? You either get heads or tails and nothing else. I mean, we're not going to count the random case that the coin stands up on its edge. So your total probability should add up to 1, whether that's 50-50 or 49-51, whatever the probability happens to be, the total probability must be 1, right? Rolling dice, right? If you have a 6-sided die, total probability must be 1. So then each of the probability for each side, probably is like 1/6. So this actually gives us some insight into the wave function, right? The total probability must be 1. So if we take a wave function, or rather take this psi star psi thing that we have, and we integrate it, right? And we integrate it over all space, that must be 1. So earlier I gave the example of, there's this little graph here, there's X and there's a wave function. And if we integrate it over these regions, we get the probability in that region. But if we integrate it over all space from -infinity to +infinity, right, we should get 1. What that means is the particle must be somewhere, right? It can't be more than 1 because I don't know what that would even mean from like a logical point of view. There's more than 100% probability of a particle. That like doesn't make sense. It can't also be less than 1. It's kind of like saying you flip a coin, 20% of the time it's heads and 20% of the time it's tails, but what's the other 60% of the time? It's unexplained. No, the total probability must always be 1. But sometimes, so that's my little 1. But sometimes people come up with a wave function, like I could make up any wave function, right? Where when I integrate, it's not 1. Sometimes it can be more than 1. Sometimes it can be less than 1. So if it's not 1, so if this is not true, we say that psi, let's write it nicer. If this is not true, like you get more than 1 or less than 1 when you integrate, we say that psi is unnormalized. And if this is true, we say that psi is normalized. So that's just the language that we used. A lot of times people just make up a function, like I would just make up a function and I don't know if it would integrate to 1 or not, right? Like I'm just making up a thing. So in those cases, my wave function would be unnormalized and then we have to normalize it. So the way that we do that, so let's talk about how we actually go about normalizing a wave function. How to normalize a wave function. So let's say you have some wave function psi, right? And this is unnormalized. Well, I can normalize it, right, by multiplying it by some number, some constant, n, times the same original wave function. So this whole thing together makes up a normalized wave function. And whatever this number n is, right, we call this a normalization constant. So we can take any unnormalized wave function, multiply it by some number to get a normalized wave function. The trick is to figure out what that normalization constant n is, right? So here's how we're going to figure out what that normalization constant is. So we know that if we take this normalized wave function, so we take this normalized wave function, which is just n times psi, and we do the psi star psi thing, right? And we integrate that over all space. This should be 1, d tau. So if the wave function is normalized, this should be 1. So we could work off of that. So n is a constant, so n times n becomes n squared. And since it's a constant, we can take it out of the integral, so we end up with this stuff. Right? And remember, we're trying to solve for n. So n squared, we divide by this part here. We're going to divide by this part here. So n squared is equal to 1 over the integral over all space of psi star psi d tau. And so to find n, we just do the square root, right? So n is equal to 1 over the square root of the integral over all space of psi star psi d tau. Another easy way to think about this is if you want to figure out how to normalize any wave function, you just do the regular probability, right? Over all space, d tau, and I don't know, let's call that integral I, right? And then if I is 1, then it's normalized. If I is not 1, it's unnormalized. And the way we normalize it is by setting n equals to 1 over square root of I. So normalization is a probability problem. The only difference here is we're going over all space, right? By all space, that could mean from negative infinity to positive infinity. So when you're integrating, it goes from negative infinity to positive infinity, right? But that's not always true. Like sometimes I will say that the wave function is only between -5 and positive 100 or something. So all space can mean literally all space from negative to positive infinity, right? So the particle is somewhere in the universe. or it can mean whatever region that I tell you. All right, so let's digest this. Normalization is a probability problem, but it's a probability over all space. We can go from an unnormalized wave function to a normalized wave function by just multiplying it by some number n. We need to find that number n though. The easiest way to find that number n is to first find the integral of this thing. If it's 1, then it's already normalized and n is just 1. We don't need to worry about n. If the integral is not 1, then this normalization constant is 1 over the square root of that integral. Make sense? Let's try one for practice and we'll see how we do. And please ask questions. But there's going to be a lot more integrals in this course before it's over. So let's normalize the wave function psi of x is equal to sine 2 times pi times x between x equals 0 and x equals 1. So in this case, the region that I want to normalize for is x equals 0 and x equals 1. So we don't need to go from negative infinity to positive infinity. It's just 0 to 1, right? So remember, we need to find this integral, psi star psi d tau, and then the normalization would be 1 over the square root of that integral, right? So just like the probability problem, we need to find psi star. So psi star of x would be this guy, just negative whenever we see I, but there's no I in there. So psi star is the same as psi, which is sine of 2 pi x. So this integral that we're looking for should be the integral over all space. In this case, all space just runs between x equals 0 and x equals 1. So 0 and 1 of psi star x times psi of x, and again dx because x is the variable we're looking at. So I changed tau to x. All right, so let's look at this integral. It's the integral between 0 and 1. What is psi star psi? Well, psi star is sine 2 pi x, and psi is sine of 2 pi x. So those two multiplied by each other will give us sine squared, right? Sine multiplied by sine is sine squared. Sine squared of 2 pi x dx. At this point, you look up the integral in the integral table, and for this in the integral table, right, the relationship we're looking for is sine squared bx dx, right, on the table, where b would be the same as 2 times pi. So substituting that out, I get, let's see, x over 2 minus 1 over 4b, but again, b is 2 pi, so 4 times 2 pi becomes 8 pi, times sine of 2bx, but again, b is 2 pi, so 2 times 2 pi is 4 pi x, between x equals 0 and x equals 1. So this integral becomes, if x is 1 here, right, we're substituting now, 1 over 2 minus 1 over 8 pi times sine of 4 times pi times 1, which is just 4 times pi. And then we minus this limit. So x is 0, so 0 over 2 is 0, minus 1 over 8 pi times sine of 4 times pi times x. X is 0, so 4 times pi times 0, which is 0. So sine of 0 is 0. So this whole thing again goes to 0. And we really like when things like that happen, because, you know, it makes our math easier. All right. So we have half, right, minus 1 over 8 pi times sine of 4 pi. 4 pi is radians in radian. Now, you don't need to plug this number in the calculator necessarily to figure out what sine of 4 pi is, right? You can just think of a little curve. Let's say this is x. Sine of 0 is 0, right? Sine of 90 degrees, which is pi over 2, is 1. And then at 180 degrees, or pi, it goes to 0 again. And then it goes down. This is 270 degrees, right? Which is 3 pi over 2. And then this is 2 pi. Basically, if you remember your sine curve, you'll find that sine goes to 0 at these points here, which correspond to either 0 or pi or 2 pi, or this would be 3 pi. Anytime it's a whole number multiplied by pi, sine goes to 0. So in case you didn't have your calculator at hand, you realize that sine of any integer times pi goes to 0, which means this whole thing goes to 0. So this integral just becomes a half. Everybody with me? Let me know if this is too slow, right? Or too fast, actually. Let me know if this is too fast too. All right, so the integral is a half. And we set up here that n is 1 over the square root of that integral, right? N is 1 over the square root of that integral. So let's find n, right? N is 1 over the square root of the integral, which is a half. So 1 over the square root of a half becomes the square root of 2. In case, and again, I have no idea what your your level of math background is, but right, if you have the square root of 1 over a half, that becomes the same as the square root of 2, right? You flip this when you put it on top. There's lots of ways to think about these math algebra manipulations. So just let me know if anything seems like a step too far and you're not sure how I got there. I don't want you to get caught up in the math, even though there's a lot of math here. So n is the square root of 2. So if we were to write the psi now that's normalized, right, it will be some number n times the psi that was unnormalized. And so the value of n was the square root of 2, and the unnormalized wave function that we started with was sine of 2 pi x. So this is the normalized wave function. So this whole idea of probability and normalization are connected. Probability is just between two regions, A and B, that doesn't have to be the whole space. Could be whatever space, some small region that we're looking at. Normalization takes the integral, the probability for all space, right? And the normalization constant is 1 over the square root of that. I only see a handful of you, but your faces look very solemn. So I don't know if that means, yeah, this makes sense, or no, this doesn't make sense. We've gone off the deep end. Let's try one for practice. Really, that's the only way we're going to know whether we have it handled on this. So let's normalize the wave function psi of x, right, is equal to, let's do sine of pi times x over 3 between x equals 0 and x equals 3. And let's see how that goes. theoretically, you shouldn't need a calculator. A lot of these problems, these calculus problems, you actually don't need a calculator. The probability ones where you have to put in a random number for x, you'll probably need a calculator. But a lot of these problems, I choose numbers that come out nicely, if you will. So you shouldn't need calculators. But you should still bring one for the exam. I want a show of hands. How many, for if you're on camera, otherwise you can like raise your hand thing. How many people don't like math and don't like calculus? Maybe 2 people who have their cameras on, and for the people with the cameras off, I don't know. Okay, so I'm guessing the majority of people are comfortable with calculus and comfortable with math. That's good. But please let me know if I need to slow down. The topic itself is hard enough as it is. We don't want the math part to be the like limiting reagent. All right, I'll give it like 30 more seconds and then we can go over it together. All right, so let's look at it. And once we start seeing equations like these and you look at it and you're like, there's no I, no complex number in there. So right away, you should just be like psi star is the same as psi, right? Like we don't need to find complex conjugate or any of that because it's a real wave function. So now this integral will be over all space. And in this example, all space just goes from 0 to 3 of psi star psi. And so it's sine of pi x over 3 times sine of pi x over 3, which is just sine squared of pi x over 3 dx, right? That's the integral we're working with. Again, we're looking up this integral in our integral sheet, and it will look like this, sine squared of bx dx. And so in our example, b would just be pi over 3, right? So you just write it out, right? It's x over 2 minus 1 over 4 times b times sine of 2bx. Let me just verify that that's actually correct. Yeah, that's correct. Going from x equals 0 to x equals 3, right? But b, as we said, is pi over 3. So b is pi over 3. Oops. And b here is pi, let's rewrite the x, pi over 3. So make sure you do those substitutions. All right, so let's see what this integral comes out to be. At x equals 3, this first part here becomes 3 over 2. This is still 3 over 4 pi times sine of x is 3, right? So it's 2 times pi times 3 over 3. And then for the second part, x is 0. So 0 over 2 is 0 minus 3 over 4 pi times sine of 2 times pi times 0 over 3, which is just 0. And again, sine of 0 is just 0. So this whole thing just goes to 0. Right? So now we need to solve this integral. So 3 over 2, that stays the same, minus, let's see what this thing is. So 3 cancels out with 3, so it's sine of 2 pi. And remember, sine of 0, 1 pi, 2 pi, 3 pi, 4 pi, all the pi's, sine of those are 0. So, 3 over 4 pi times 0 is 0. So this part goes to 0 as well. So the integral is just 3 over 2, right? The normalization constant is 1 over the square root of the integral, which will just be, in this case, 1 over the square root of 3 over 2, which just becomes the square root of 2 over 3, right? I just flipped it. So that's the normalization constant, but the question asks you to find a normalized wave function. So psi, I'll put normalized up here. Or bottom, I don't know, let's put it in the bottom. It's just a label. I want to label this wave function as being normalized. Put it there. So the normalized wave function becomes this normalization constant, n, which is square root of 2 over 3, times the original unnormalized wave function, which was just sine of pi x over 3. Sine of pi x over 3. Did everyone get that? Or close to there? Or if you didn't see where you probably made a mistake? Yep. No, please ask your questions, right? There's another example in your textbook that I didn't go over because I like to leave those examples alone, so you have another example to look at. And then there's end of chapter problems you can look at. By Friday, again, when I send over that checklist of what to study, I'll send over a list of practice problems so you can keep practicing. But what questions do you have for me on any of this?
How can you tell if a function's already normalized?
You can't.
can't.
You have to do this integral here, right?
Mhm.
And if the integral comes out to be 1, then it's
Then it
normalized.
is. Okay.
Now, sometimes when people tell you a wave function, like the wave function is whatever, they might tell you the normalized wave function is whatever, or they might tell you the unnormalized wave function is whatever. So they can specify, and you will then know, oh, you're talking about a normalized one, so I don't have to normalize it. If they tell you it's unnormalized, then you know right away, oh, the first step is to normalize it.
Okay.
Right? Because a wave function that's not normalized is not really complete, right? You have to normalize it and then it becomes complete. Like it becomes ready for use. So if they don't tell you, like if a problem doesn't tell you, you can assume that it's not normalized and you want to do that integral to check.
Okay.
So yeah, but if they specify normalized or not normalized, then you know. But yeah, I would say it's safe bet is to assume that any wave function anybody gives you is not normalized. What I'm trying to think of here is sometimes I just make up wave functions and they're not necessarily going to be normalized, but I don't want you to waste time normalizing it. So I think if for an exam, for example, if I specifically want you to normalize something, I will let you know. I will either let you know by saying normalize this wave function, or I will say the unnormalized wave function is something. So if I tell you that the wave function is not normalized, your first step is to normalize it. Does that make sense?
Mm-hmm.
Yeah. Otherwise, if I just give you an equation and tell you to find a probability, for example, I don't want you to waste time normalizing it because that's not the aim. The aim is to find a probability. Right? I want to keep questions like just small and contained into like one problem at a time. But that's a great question. All right. So what have we learned so far? So far in this chapter. So we talked about the fact that matter needs to be described as a wave based off all of the experimental evidence. So we need waves. And the first postulate of quantum mechanics was to describe matter using this wave function psi. Again, this is just a symbol, but we need symbols to represent things. Otherwise, we don't know what we're talking about. Now, for classical physics, right, I gave this example of like a bouncing ball where you have a ball and this could be, let's say, some function of x and height, right? This is x, this is height. And what this function means, you can pretty much see it, right? This is the ball. This is the path the ball takes when it bounces. Right? It's pretty obvious when you're looking at classical physics. But in quantum mechanics, you have these random wave functions. Well, this is not valid, but you have a wave function, you know, but we don't know what the wave function means. It's just a function that describes something about the particle. But all we know is everything about the particle is inside of this wave function. This wave function tells us everything we'd ever want to know about the particle, but we actually don't know what the wave function itself means. Now, Bohr was like, forget the wave function. The square of the wave function, psi star psi, that's probability, right? So just by recognizing that psi star psi is probability, we know a few things. We know that probability must be 1 over all areas, right? So we can normalize wave functions. All right, so that's it for wave functions. We also postulated that we should have operators and observables, and really the only thing that we can observe are eigenvalues from eigenfunctions. And that's where we are right now. We have wave functions, they can be normalized, and we have operators and they can give us eigenvalues. But so far, we haven't discussed what this wave function should even look like. And how do we even get it? Like, I can draw any wave function as long as it satisfies the requirements that I talked about. Remember earlier, it must be continuous, must have a differential. I forgot. Continuous differential
Single
must
valued.
not go to infinity. And sorry?
Single valued.
Single value. Thank you. Single value must not have multiple values for the same value of x. But we really don't have a way to figure out what it is. And that is where the good old Schrodinger equation comes in, which I'm sure many of you have heard of. So the Schrodinger equation. And I know we don't have a lot of time left, so I'm just going to set this up and I'm going to come back to it next time. But we don't have an understanding of what the wave function psi should be specifically for like specific particles, right? So that's what we're going to talk about in this section. So let's write the objectives. I like to write that. Here we're going to be able to write the time independent Schrodinger. There's a little double dot over the O, right? I write, let's make it clear that the double dot is over the O. I think it's German or something. I don't know. So you should be able to write the time independent Schrodinger equation. And sometimes I'll just write SE for Schrodinger equation, right? And I also want you to find the energy eigenvalue from the Schrodinger equation. All right. So we have psi as a representation of something about the particle, but we don't know what it is. We have rules for psi that they can be single valued, continuous, and so on, but that doesn't tell us what shape it should take. We also have rules for operators and eigenvalues, but none of those tell us what shape psi should take. And we also have even more rules governing normalization, but none of that still tells us what shape psi should take. Like, I could draw any wave function, right, as long as it's valid. But how do we know which one's which? How do we figure out what the wave function is? And that's where the Schrodinger equation comes in, like I said. And if we're like, if we're going off of classical mechanics, let's look back at this bouncing ball example, right? I just drew a random equation for a bouncing ball somewhere. Where? Here, right? But I mean, how did I know what shape that bouncing ball would take? Well, here I would have to solve some equation of motion, right? Either Newton's or Hamilton's or Lagrangians, one of those equations of motion, I will probably plug in the force of gravity going downwards and maybe plug in like the initial velocity, right? Like the ball had a push forwards, that's why it's bouncing forward. And maybe there's some like air friction or some, like I'll have to plug in all of the forces, right? But once you have the forces or the energy or any of that stuff, I can solve for the equation of motion and I get literally an equation of motion that shows the motion of the ball. Yeah? Well, what if we do the same thing for the wave function? Let's plug it into an equation of motion and see what motion we get out of the wave function, right? Now there's 3 different types of equations of motions we could use here because we studied 3 different types. Newton's, Lagrangians, and Hamilton's. But like I said, Newton's require forces and we don't always know the forces, and it really only works well for straight lines, and electrons are not going to move in straight lines. Lagrangians work with energy, which is good, but Lagrangian is kinetic energy minus the potential energy, and that's a weird thing to think about. But Hamilton's is interesting because it's kinetic energy plus potential energy. So we know that this is total energy. And that's very useful for us. So what we need to do is plug our wave function into a Hamilton's equation of motion setup. And really, that's all Mr. Erwin Schrödinger did to come up with the Schrödinger equation. He plugged the wave function into Hamilton's equation of motion, and he created his fancy equation. But seeing as now time is up, we're going to continue that where we left off. I hopefully just whet your appetite about the Schrödinger equation, and we'll get back there. Next class, which is next Tuesday. Any questions or no? Yeah. Please ask them. All right. Well, if you think of any, just let me know. Nope, we lost a person. Yeah, if you can think of any, just let me know. Otherwise, I will see you next Tuesday. And remember, next Thursday is the exam. We're not meeting this Thursday. All right. Enjoy your break. I'll see you next Tuesday.
Hi, Doctor. Can
Yes.
you go up for a note a little bit?
Yeah, sure.
Just go it up a little.
All right. Which one are we looking at? Or do you want to share your screen so that I can see what you're working with?
Wait. I can share my screen. Let me try. Can you see it now?
Yes.
So I don't know what happened to this thing. It doesn't let me do it.
So click in there, or click the play button to the left. That's to run it. Let's see what happens. And let's scroll down to see what the error is. Okay, so when these things happen, like name error, it means that you lost connection and you need to reconnect. So here's what I'm gonna do. Go to runtime, the menu on top, runtime, and then let's see, just hit run all. There it is. What it means is that whenever you restart, remember you have to run all of the cells before that comes before everything would work properly. So it just means that you lost connection and you need, yeah, you regain connection. Now look at the top there. Do you see cannot save changes?
Yes.
Did you make a copy of this in your own?
I make a copy right here. That's fair.
So when you say cannot make same changes, it means that you're not working with your own copy. So here you can go to File and save a copy in Drive, for example. And it'll open in a new tab. Yeah, and make sure just like name it something that you'll be, you know,
Okay.
that you remember.
Yes.
Okay.
Thank you.
So is it, which one is this? This one still says cannot save changes. So you want to close this one.
Okay, this one.
This one is the one you're working with. So close the first one.
Okay. And I have, I think, one like small question.
Mhm.
I don't know which one is that one. Mm, so this one,
Mhm.
I don't know. Like you say, like put two momentum wave functions together. So
Yeah.
just that. This is that right? That it for this part? Because I only
Mhm.
see like one thing, so I don't.
Yeah. Yeah, you add the two of them together and you get one function out of it.
Oh, okay, okay,
If you add three of them together, you'll still get one function out of it, but it's like the three of them added together.
okay. And my question for the other one was, wait, did we talk about this one? Oh yeah.
Yeah.
Okay, okay.
So if you scroll up for a second, go back to where you were and scroll up here, right?
I'm gonna go like to code.
Wait,
Oh,
hang on.
hold
You can delete that for a second. Click in the box that you just had. Where you're scrolling too fast. I don't know.
right here.
Here, yeah, right. Um, so remember I mentioned that we shouldn't do psi integrative psi. It should be psi star psi.
So side.
So if you go to your ACE stuff,
Yeah, yeah. Okay.
there's a correction that you need to make, right?
Yes.
So just remember to make that correction because, but yeah. So once you made that correction, you just add a code cell, copy and paste it, like each the separate ones below.
Okay. Thank you.
But yeah, remember to make that correction.
Yes, I will do it. And now, can you go back to your note a little bit? I
Yes.
will miss like couple of spots.
Which part?
Going up and up. Go up a little more. Right there, right there. Right there. So these lectures will also be recorded, right?
Yes. Hang on. Is it still recording?
Um,
Yeah, it's still recording. Yep, it's still recording. I'll keep all of this in the recording. That's fine. Unless you want me to stop recording. But yeah, we're still going.
Okay. All right. Thank you.
All right, I'll post this recording on ACE, right? On their lessons. I usually just post it. So you'll see it there. Sounds good? All right, if you have any questions, just let me know. Otherwise, I'll see you next Thursday.
See you.